Hello and welcome to Haybridge Maths Department, Year 2 Pure, and we're looking at Chapter 3 series, and today we're going to be modelling with series. Now this is a big old section of the course, modelling, and it crops up in lots of different areas. We need it quite a bit for this new course that's been used, and that definitely is the case with sequences and with series. We've got some big examples for you today. So what I'm going to do is I'm going to split this up into two videos. Of course, I want you pausing and rewinding if you don't understand something. Hopefully you don't fast forward anything. But even with that, with the fact that I know that you're going to be pausing and rewinding, we're going to make this into two videos so that it isn't too long all in one go. Okay, so let's get started actually with a starter. What I would like you to do is I would like you to find the sum to infinity of the following series. So pause the video again and get started here where we will find the sum to infinity. So off you go. Okay, so let's have a look and see what you should have got. Now, if you remember from a couple of lessons ago, the sum to infinity is given by the formula. Oh dear. Let's just rub that out. It's given by the formula A over 1 minus R. Now, in this case, we can see that A equals 9, R equals 0.1. So if we plug this into the formula here, then we will have 9 over 1 minus 0.1. So it's going to be 0.9. So 9 divided by 0.9 gives you the answer of 10. So if we want to find the sum to infinity, you get the answer 10. But hold on. If you do 9 plus 0.9, you get 9.9. You add on another 0.9, you get 9.99. Then you get 9.999. 9.9999. 9.9999. And we keep going, and you're just adding on however many zeros and then a 9. You're just going to get eventually, aren't you, 9.9 recurring. So what we're shown here, and I think you probably have seen it before because I know that us maths teachers like to demonstrate this, but what we've got here is another way of showing you that 9.9 recurring is the same as 10. It's another one of those mind-blowing demonstrations where you go, well, how are the two things the same? But there's many ways that we can show you, and here is another. Right, so there's a little starter to get us started. Let's get on with the main course. Let's get on with an example where we model an arithmetic series. Here we go. So it's a big old question. This is. It's from the textbook, and it's all about somebody called Bruce. And what he does is starts a business, and in the first year he gets 20 grand of profits. And then he thinks each year what's going to happen is his profits are going to go up by 5 grand. So in the second year he reckons he'll get 25 grand. Third year he'll get 30 grand, etc., etc., until he reaches 100 grand. At that point, he'll keep on making a profit, but his profit won't go up, and he will keep on making £100,000. What we want to do, at least in part A, is work out how much profit Bruce makes in the first 20 years. Right, this is not a straightforward arithmetic series problem because you are going to have two bits. You're going to have the bit which is where the money is increasing, the profits are increasing, and that will be an arithmetic series. But then you're going to get to a point and you're going to keep on having to add on £100,000. So if we look at it like this, we're looking at the sum of the first 20 terms, then you've got 20,000 plus 25,000 plus 30,000, and you keep going until you get to 100,000, and then we keep on adding on 100,000 until we get to 20 terms. So the key to all this is first of all working out how many terms in are we for this term here. And we're going to use our general form for a term in an arithmetic sequence to work this out. So if we say for this term here, we just put a little star here, then we can say that UN is A plus N minus 1. D, 100,000. A is all the way over here. It's this 20,000 here. And we've got plus N minus 1. And D, well, it's going up by 5,000 each time. Right. 100,000, take away 20,000, 80. Divide by 5,000, you get 16. So you get N minus 1 equals 16. So we get N equals 17. Right, okay then. So we know that the last term in the arithmetic series, the first point where he gets to 100 grand, is going to be the 17th year. That means he's got the 18th, the 19th, and the 20th year where he makes another 100 grand each year. So this sum of the first 20 terms is going to be n over 2, and I'm going to use this form of a formula, a plus L. So that will be up to the 17 terms, and then we're just going to add on 100,000 times 3, because we're going to do 3 lots, because you're going to do the 17th, you're going to do the 18th, sorry, the 19th, and the 20th. So let's sub in our values for the series. So you've got 17 over 2 20,000 plus 100,000. So that's our first and our last. 20,000 being the first, 100,000 being the last, and then we're going to add on 300,000. It is just a case of substitution into your calculator, and at this point you will get 1,320,000. Okay, so a bit more complicated than your standard arithmetic series, but it is the case of making sure that you spot it's that term where it flips from being a series to just a straightforward add on 100,000. Once you spot that you need to work out what that term is, the problem gets a lot easier. So if you would like to make some notes on what I have done here. And then let's have a look at part B. State one reason why this might not be a suitable model. So we've got to reinterpret what's happening in the question. It's not just a case of being able to do some number crunching. In the exam, you'll be expected to interpret your answers, not just in applied, where this will happen more often, but also in pure. So in part B, well, what's going to happen is profits are going up by 5,000 each time. That doesn't tend to happen in business. Things don't tend to go up by the same amount. What you have is an accumulative effect. So as you get more, it's easier to acquire more. It's called the Matthew effect. It's been around for a couple of thousand years, but it's everywhere, and it's certainly true in business. You wouldn't expect the amount that he makes or the profits he makes to go up by the same amount each year. So one reason why it might not be a suitable model, profits will unlikely rise linearly or in a linear fashion, or whichever way that you want to do this. Okay, so what about part C? So Bruce decides to employ the services of a financial advisor who laughs at his model and comes up with a new model. And he says, you know what, it's going to go up by a percentage amount each time. So what's going to happen is we're going to say that it's going to go up by 5% per annum, which is pretty good going. And now we're going to use his financial advisor's much more sophisticated model to work out the sum of the first 20 terms. So here, sorry about that, let's just rub that out so it's a bit clearer. Let's put this one in. If we're looking at the sum of the first 20 terms, let's just look at how the series starts off. So we start off with 20,000 plus 20,000 times 1.05, because that's going to go up by 5%. And we're going to go 20,000 times 1.05 squared, and you're going to keep going. And you're going to get to 20,000 times 1.05 to the 19. It's always one less, isn't it? The power there. Right, okay, so you have, in this situation, A equals 20,000, R equals 1.05, and there's 20 terms. So we now need to go back to our formula for some of the first 20 terms, and we need to say that the sum of the first 20 terms is A r to the n minus 1 over r minus 1. Plug those values into my formula. So we're going to get 20,000, 1.05 to the 20 minus 1 over 1.05 minus 1 . And if you plug that into your calculator, apparently you get 661,319 0.08. So you get all this money here. He's going to make 661 grand over 20 years. Pretty good going. But it's not quite as much as he thought he was going to get, where he thought he was going to make over a million, well over £1 million in 20 years. It would be really good going. So Pfizer's turned around to him and gone, look, mate, you've done all right. You're going to do all right, but not as well as you think you are. Okay, what I'm going to do, hopefully there's no mistakes there. Do let me know if there are any, but otherwise I'm going to leave it here. I'm going to stop the video, and then you can start back on the next video where I will be giving you this question to do first of all. So if you want to, pause the video at this point, have a go at the question, and then restart the video, or restart the video on the second video now and have a go at the question then. You're cool. All right. Thank you very much. Goodbye.